Yes, sir. I have started the recording. Yeah.
Okay, all right. Okay, so students, once again, thank you for joining and sorry for the interruption in the beginning. Uh, I was using IIT network earlier, but I think it was breaking like every few seconds. So I switched on to a mobile network, and let's hope it goes very well. All right, so let me share my screen and talk about today's class, which is a third class in the series now, and we are talking about projections of points and lines. We talked about last class simple projections, but we'll now go into even how do you draw those projections. Too many interruptions again. Yeah. Let me know you're able to see the full screen now, hopefully. Okay.
Yes, sir. It's visible.
Yeah. All right. So let's go. So what I'll do is let me start very simply saying why do we even need to look at projections of points and lines? Now, any object in real life is three-dimensional. Okay. Even a so-called 2D object is a 3D object because it has some thickness and it is oriented in space in some way, right? Special cases are when it is a flat object and it's oriented to a, let's say, plane, orthogonal plane, or whatever that you want to talk about. So in general, eventually we'll have to worry about if you are able to see a object in a 2D view, in an orthographic 2D view, like we saw in the previous class, we should be able to visualize and reconstruct or draw the object in 3 dimensions also. I mean, among many examples, one example which you see here is, of course, the pipes, right? And pipe network in a chemical plant. A pipe can be represented by a line, let us say. And then you're drawing these lines, and these lines are all over the place in 3 dimensional space. Not all lines are either parallel or perpendicular to each other. Some of the lines may be inclined also, as you can actually see in this picture. A few lines are inclined. Now, given all those things, how do we even visualize the entire chemical plant with all the pipes, even is represented as lines, for example? That is one example. One another crude example I'll give you is that when you go to a hospital and you get a CT scan done or MRI scan done, for example, those scans are in 2 dimensions. And those scans are not only 2 dimensional, they are lines decomposed into pixels. Finally, it is nothing but dots, right? Each X-ray beam is giving a dot or inside your body. And how do you reconstruct all those dots into a 3 dimensional model? So all said and done, the visualizing from a 3D object to 2D views, like we did last time in the last class, and you did a lab class also on last Thursday. We are now talking about the reverse, which is that given a 2D view of an object, how do you visualize that or reconstruct that in 3 dimensions? And if you take the same chemical engineering problem, one of the things that you may want to solve as an engineer is, in case one pipe is carrying a hot water, another is carrying a cold water, you want to know what is the distance between the pipes. And let's say both pipes are inclined to orthographic planes and inclined to each other. You still want to know what is the minimum distance between the two lines and how do you do that in 3 dimensions. Okay, so minimum separation between them. So we want to see what is the heat transfer taking from a hot pipe to a cold pipe or vice versa. So things like that problems come up in engineering, and you need to know these projections of points and lines. One of the other many things that you have to worry about is in a 3 dimensional line, and let's say its coordinates are x1, y1, z1, and x2, y2, z2, and let's incline to all the orthographic planes. Orthographic planes meaning xy plane, yz plane, and zx plane, all of which are perpendicular to each other. You give a line in 3 dimensional space, which are and the line is inclined to all the three planes. Okay, and let us say you're able to see the line only in a 2D view, let's say XY view or a YZ view or a ZX view. I'm just saying plane or view. Then what is its true length in 3 dimensions? You can say, why are we even talking about something silly like this? Because given x1, y1, z1 and x2, y2, z2, you can always find the true length by calculation. But we are talking about also now doing that in a visualization mode in a graphical manner by drawing the whole thing. So it's all about, again, you can calculate, and of course, if you use computers, you can also calculate that automatically. But this is to help you to develop the skills to visualize 2D to 3D and 3D to 2D and so on. Okay, so we'll talk about what is the projections of a line in a 2D plane, and when it's projected, its line's length changes. So what is its true length and how do you determine that and so on. Those we'll discuss in today's class. So let's also talk about some conventions before we go too much ahead into that. So let's say the point A, which you see in the red circle there. And let's say that, and similarly, you can have point B, point C, and we will put up some of those points. When you project the point in the horizontal plane, okay, we will call it as a small a. This is a denotation, it's just a notation. And if you look at the Andy Bhatt book, this is following the exact notation. So in case you go back to the book, at least you know what I'm talking about without getting confused. So if you take a point A, capital A, its projection on the horizontal plane will be denoted by small a. Okay, and its projection on the vertical plane will be denoted by a dash. For the moment, just remember these two only. Let us not worry about side views. And later on in the course, we may also talk about auxiliary views, which have different notations also. We will not talk about that for the moment. Okay, we'll just talk about, let's say, capital ABC, which is for the point, small ABC for the horizontal plane, which means what? Top view. And A dash, B dash, C dash for the projection in the vertical plane, which is nothing but the front view. Is that clear? On the right side picture, if you see small one, the XY plane, there is the first quadrant, and first quadrant, you're rotating the horizontal plane. Always, when you to get the views, you take the horizontal plane and rotate it in a 90 degrees clockwise direction. That is how you get the top front, both the views drawn in a sheet of paper. Okay, so when you rotate the HP comes below VP, and the VP you're projecting essentially the front view. So front view comes on the top, and then you're rotating down. So the horizontal view, which is nothing but the top view, comes below the front view. So what did we say? The front view rotation is A, and the top view, sorry, the front view, the top view rotation is A, which is coming below here, and the front view rotation of the point is A dash, which is coming above here. Just keep it, fix it in your mind, and then so when you go ahead, a little bit more complex also, you'll still be able to understand what I'm saying.
Excuse me, sir.
Yeah, please.
Sir,
Go ahead.
could you please use annotation to explain this once again?
Okay, so I'll also do my laser screen. I forgot now how I did that. Did I do arrow option? No.
Sir, the
What's
third option on the screen.
Third option. Yeah. Laser pointer. Thank you very much. What I'm saying is we are talking about point A. Its projection, which is nothing but in the horizontal plane, will be denoted by small a, and its projection in the vertical plane will be denoted by A dash. In other words, point A is denoted by A in the top view, which is nothing but the HP in horizontal plane is top view, and is denoted by A dash in the front view, which is nothing but the vertical plane view. And vertical plane is coming below horizontal plane because whenever you want to get both the views on a sheet of paper in a two-dimensional space, then you always rotate the horizontal plane clockwise, right, like this, to make it vertical. So vertical plane is coming above horizontal plane when you draw the actual views, right? Front view is coming above the top view. And what I mentioned is A is the top view, small a is coming below A dash, which is the front view of the same point A. I think that's clear enough, right? Now let us go into the projections of points in different quadrants. I'm starting from the same first quadrant, so there's no confusion. This is exactly same as what I said earlier, right? There's no difference in that. Okay. Now we'll go into other quadrants. This is the quadrant number 2 because points can lie in any quadrant, right? Our views, we're talking about first angle view and third angle view. But as far as points, they can lie in any quadrant. So when let us say point A is now lying in the second quadrant, okay, which means and always I have to get the view, but I mentioned that horizontal planes will always be rotated in a clockwise direction. So what will happen? This plane on the left side will come vertical, and this plane come below, and that is what we should look at the projections of the point. Let's look one by one. So if you look at the projection of A on the vertical plane and projection of A on the horizontal plane, right? Let's look at the projections first. So projection on the horizontal plane is small a, on the vertical plane is A dash. We talked about that. But when you actually draw the points or pinpoint the points in both the views, what is happening? You're rotating the thing. So vertical plane remains vertical, no issue, but the horizontal plane is rotated. So horizontal plane now coincides with the vertical plane. Okay, coincide means even in the same location. And so what happens? Your in the vertical plane, which is a front view, A dash is fine, which is already there, but the projection on the horizontal plane, which is small a, also rotates and comes below A. So, right, it comes below A. So essentially, the projections of the point A, capital A, in front view and top view, but point A, the point capital A is lying in the second quadrant. Its projections, both projections in the front view and top view, lie on the same side of XY line. Very clear. Again, I'm not saying something rocket science. It's just a question of fixing in your mind what is happening. Let's go to now the third quadrant. You know?
Excuse me, sir.
Yeah.
Sir, just to confirm, so we rotated this horizontal plane so that it coincides with the vertical plane in this way because we have to rotate it clockwise only, right?
Yes, yes, yes. Okay.
Okay, sir.
Now look at the third quadrant. Just mental exercise, right? All these are.
Hello? And we can only rotate it once?
Yes.
Like we, okay.
Yeah. Only by 90 degrees and not more than.
Okay.
All right. Thank you for that. Thank you for asking the question. Now let us look at the third quadrant. Okay, let's call it as a C for a change. Its projection on the horizontal plane is small c. Okay, projection on the vertical plane is C dash. No problem. And when you turn the horizontal plane, what is happening? Okay, the projection on the horizontal plane was C, right? So C is coming this way, right? So C is coming above, and your C dash anyway was on the vertical plane, which was below. So now C is on the top. So in the third quadrant, of course, this is how it was. You know, if you remember our third angle projection also very neatly. The small c, which is supposed to be the top view, is coming on the top, and c dash, which is supposed to be the front view, is coming below the top view. Okay, I said conveniently because top view on the top is somehow mentally easy to understand. It's just that India has adopted the first angle projection, so we have to kind of live with the top view below the front view. Okay, as I said, I personally prefer top view on the top. So if in the examination there is no choice, they say, okay, you draw any view, any quadrant or any angle projection you want, you may use your own preference. But India, remember, the drawings will be always top view coming front view. So you have to at least mentally prepare to understand the drawings. But you know, eventually when you draw those top view, front view aligned with each other, you know, it's not very difficult to mentally juggle, okay, if top view hai, ye front view hai, it is not a difficult thing. It doesn't matter really if it's third angle or first angle. Okay, so let's complete this exercise. So and let me put the fourth quadrant. And now I will not say anything. You just mentally think what I said earlier, the rules of the game, and understand the fourth picture, which is the point lying in the fourth quadrant. I'll just give it 30 seconds for you to understand it yourself. Okay, you are fine. So now horizontal plane is to be rotated and it will coincide with the vertical plane in this case. But before you rotate, first do the projections. Always project first and rotate later. So if I'm talking about point number E, its projection on the horizontal plane, which is top view, is small e. Its projection on the vertical plane, which is front view, is E dash. And for drawing the points, I have to rotate the horizontal plane by 90 degrees. So both E and E dash will come on the same side of the line. And depending on the distance of the point E from the vertical plane and the horizontal plane, E and A dash can be above or below each other, but both will be below the XY line only. Right? And always remember XY line as an intersection between the vertical plane and the horizontal plane. Okay. In other words, the horizontal plane is seen as a line XY in the vertical plane. I'm saying something important. Just listen carefully. It looks very banal. Banal means something no big deal, you know. But just listen carefully. In the top view, okay, vertical plane looks like a line. Vertical plane is a plane, right? but it looks like a line XY in the horizontal plane. Similarly, the horizontal plane looks like a line, XY line, in the vertical plane. Okay, just remember this very standard statements because we'll use it in the next part of this today's class. But just for your quick summary, and I just put only one point here, which is for the third quadrant. Just look at this slide, and this is just to re-emphasize whatever I just now told you. No difference. Okay. Additional point here. Front view and top view of a point are always on the same vertical line. True or not, right? You saw all the pictures earlier. Whenever you saw E and E dash, C and C dash are always on the same vertical line. Just remember that point also. Again, it will come in very handy when you go into complex things. Okay, and distance of a front view of a point from XY. Okay, distance of the front view, which is in the vertical plane, which is C dash here. Distance of the front view of a point from XY is distance of a point from the let me just get it, see if I put it wrongly here. Give me a second. Distance of a, just check the this point, statement number 2 and 3, are they right or wrong? Okay, please help me out. Distance of the front view of a point. Front view of a point is essentially on the vertical plane, which is C dash. Okay, from XY. So C dash from XY is this. Distance of a point from horizontal plane. I am not sure this is correct.
It's correct.
Correct?
It's
Correct.
correct.
Yeah, it's from O to C dash.
Yeah.
C dash on this plane. I'm sorry. Yeah. Okay, so I was looking at this wrong direction. I should go to CO, not CX. My mistake. Okay, so that is nothing but a distance of point from the horizontal plane. This distance, right? And similarly, distance of the top view of the point, which is top view is your C from XY, which is nothing but CO. Okay, is distance of the point on the vertical plane. Again, same thing. No confusion in the class. Everyone is clear. Shall I go ahead? Okay, maybe one small quick exercise just to completely iron out in your minds what you're talking about. Let's say that a point A is 20 millimeters below the horizontal plane, which is your this plane, and 30 millimeters behind the vertical plane. In other words, the distance A small a is 20 millimeters, and the distance capital A small a dash is 30 millimeters. Just on your sheet, rough notebook, draw the projections of the point on top view and front view, and this time you mark the distance also. Write 20 millimeter, 30 millimeter also. 30 seconds, quick one. Okay, all of you are done. Let me see what is happening in my chat box. How do I go to chat box? Okay. All right. Just say something so that I know that you are doing something. Done? Everyone is done? Or put your thumbs up symbol. And I'll put a solution just so we can cross check that. Any thumbs up symbols? Those who have done it? Prabhat, you have to keep telling me once in a while bandwidth is okay or not.
Sir, it's a bit lagging. Like
It's lagging, so I'll just switch on the camera. In that case.
People
Yeah,
are
students,
like-
if you just do it, just put a thumbs up symbol.
yeah, they are putting it.
Able to see that then. I'm not able to see any chat in my. Okay. Right, so let me put the solution. Okay, let me put the thing. So maybe if it looks like this, give yourself a thumbs up to yourself. Okay, so let's move ahead. So with what I told you just now, let us start looking at a line now. Okay, a line you treat it as a nothing but a comprising of two endpoints. Now we're talking about A and B. Okay, so two endpoints A and B are a line, and will be start from a simple line, a line which is now parallel to both vertical plane and horizontal plane, but not coinciding with XY line. It is away from XY line, but it is parallel to XY line, and therefore it is parallel to both horizontal plane and vertical plane. Okay, the line AB. It has a distance of small d from the vertical plane and a distance of h from the horizontal plane. Okay, now look at the word new term which I'm introducing now called as true length. A true length of a line, and we're talking about two lengths. We're comparing the actual length of the line, which is a true length, to its projected lines. What is the projected line? This is a first angle projection. So the projection of the line AB, capital A, capital B, on the top view, which is below the front view in the first angle projection, is small a, small b, and its projection in the front view, which is the vertical plane view, is a dash b dash. Very weird. What happened to my laser pointer? Okay, yeah. So okay, I'll not repeat that. So basically, the line AB, which is capital A, capital B, its top view projection is small a, small b, which is a distance of d from the vertical plane, represented by line XY in the top view. Similarly, the same line AB, capital A, capital B, is represented by the line A dash B dash in the front view, and the projected view A dash B dash is at a distance of h from the horizontal plane, represented by line XY again here. So same XY. Okay, no confusion anyone, please. Okay, now we will start making life little complex for fun. Okay, otherwise what is fun in life? Now what you say is this line is parallel to the vertical plane. Okay, so this plane and this line AB are now parallel and inclined to the horizontal plane. Let's say by an angle theta. Okay. Now just think about its projections. The projection of a line AB on the horizontal plane, that is the top view. So A projects to small a and B projects to small b in the top view at a distance of d from the vertical plane. Similarly, projects to A dash and B dash, and now this is no longer parallel to the XY line, it is now inclined at some angle theta, let us say, to vertical. Now interestingly, and note my statement, because this line is parallel to vertical plane, it doesn't matter its true length and its true angle, both are same actual line as well as this projected line in the vertical plane. Okay, not in the sorry, true length of line seen in the front view is wrong, right? Prabhat, this is a wrong statement, right? I'm sorry, it's correct. I'm sorry. Okay, I keep getting confused about the front. So front view is this one. I should start marking FV there. That is no issue. In the front view, this line, the length of a line and its true length both are same because the projection is parallel to its projection is parallel to the vertical plane. So there's no difference in the true length and the projected length. Okay. What you see is that there is a difference in the top view because if you look at angle theta and you know your geometry, this will be your AB cos theta, right? So cos theta is always less than 1. And so what will happen is your projected length of AB, which is AB, small a, small b, will be less than your true length of AB. Okay. Similarly, we'll do the reverse now. Okay. Which is now we are making the line parallel to horizontal plane. Okay. But inclined with respect to vertical plane by an angle phi. Convention. Let us use theta for inclination with the horizontal plane and phi for the inclination with the vertical plane. Just again, if you go back to the book and depart, you don't confuse between phi and psi. Now same thing again. So how do you draw the projections lines here now? Again, this is I think not correct. It should be a little away from this. Maybe unless it is touching the line. Okay, then it is no issue. If A is touching the vertical, it's not touching the vertical plane. It is a distance of D. Prabhat, what is this here? This D should be on this side, right? Will I correct this? This D should be here, right?
Yes, sir. Yes, sir.
I'm sorry about this.
That XY line, yeah, that XY line will move up, like a little bit up.
Something like that. Okay, so I'm just I'm not fully correcting that, but let's say that like this, and this will be like this. Okay, and this will be the angle with the this is what happens. I think this line, there's one more line there. Right, we are trying to animate these pictures because book is static, and obviously some of those errors came in. Now let's go back. So what we're now seeing is just mentally map the whole thing. Again, this head should be sorry. This is your hedge. Okay, may not be exactly good, but actually what happened, I could have just moved the XY line and that would have been far more easy. That would have been smarter for me. Maybe I should still do that. What I need to do is this line, you can move it here. Am I right now?
Yes. Yes, sir.
Yes, sir. This smarter way of doing
Yes, now it is right.
I should have done that. Okay. So. Okay, so okay. All right, now. Okay, this is, I think by now I think everyone is clear about what I'm doing here. This is a line which is parallel to horizontal plane and inclined to vertical plane. So in the in your front view, because it is parallel to horizontal plane, in the front view we'll see it as a line parallel to your horizontal plane, which is XY line here represented here. And in the top view, you will see the line as it is inclined. But here also the true length of a line in the top view is same as your actual length, because it is the view is parallel to your horizontal view, right? And projected view, which is in the front view, will be less than your actual length, true length of the line. Now we make our life, before we make it life really complex, let's just look at this. So parallel to the plane, if the line is parallel to the plane, its true length is same as its projection length. If the line is normal to the plane, it becomes actually a point, right? Okay. If the line is normal to a plane, what will happen in the projected projection of the point of the line on the plane will become reduced to a point. And if it lies in the plane, then its projection and the true line are same thing, right? It's same. Now we will. Yeah, it's same as what I have written here. When the line is parallel to a plane, its projection on that plane, if the line happens to be parallel to the plane, its projection and the true line are the same. No discussion there. Now we will make our life a little more complex. Let you to absorb the picture first. Yeah. Yeah, go ahead. Should I go
Sir,
back to it?
can you go to the last slide?
Yeah.
So here in the second row, it says that if the line is in the plane, then its projection in the same plane will have the equal length. So that is right. But it's written that, okay, it's the other plane. Okay, sir, got it.
No problem. Now let's just absorb this picture a little carefully. First, just look at the position of XY. Look at the line. Line is now inclined to both vertical plane and horizontal plane. Okay. And therefore, and how do we actually get this ball rolling? Usually in problems, what they will give you and what we will give you for your home exercise and your next lab class, we will either say that we'll give the coordinates of A and B. By coordinates, I essentially mean that we'll say that A lies 20 millimeters from the front view or 30 millimeters from the top view, and its point B lies 50 meters from front view and 40 millimeters from top view, something like that. Basically, we'll give you the coordinates, XY coordinates of A and B, AB line, capital AB line, or we may give you the coordinates of only the AB line, sorry, of only the point A, capital A, and say that the line AB is inclined 30 degrees with vertical plane and 45 degrees with horizontal plane, things like that. But always we'll say it is inclined with the vertical plane and horizontal plane in this next exercise. Okay. That doesn't mean its true inclination may be quite different. You know, your with, let us say, in 3 dimensions. We will not talk about that for the moment. We'll just talk about the inclination of a line with respect to the vertical plane and horizontal plane. Okay, so let's look at this now.
So,
and the angles are marked here right now.
Sir, a question. You said when you give the coordinates, you'll say suppose that A is 30 centimeters from the top view. What does it mean to be 30 centimeters from?
Yeah, okay. We'll also say, sorry, thank you for it. We may also say 30 millimeters above the horizontal plane, or 50 millimeters behind the vertical plane. So we always tell you that, so we can make out which quadrant it lies in. Okay, so it's, in a sense, it is in a mathematical terms, we'll say it is minus, XY coordinates. Is it minus or plus? Because origin is lying in the intersection of the horizontal and vertical planes, right? So we'll always tell you not just 30 millimeters from HP, but also we'll say 30 millimeters above HP or below HP also. So not to worry about it. Okay. I think that clarifies your doubt, right?
Yeah.
So yeah, good. All doubts are valid, by the way. So thank you for asking this. And that clarifies for someone else who are shy of asking doubts. Okay, fine. Now let's look at carefully and let's look at the projections now of this thing. Okay. So what we said is that let us say point A is defined. So we know exactly its distance from the XY plane in the front view and the top view. That you can always, so you can mark the point in the drawing sheet. No problem. And let us say we told you that its angle of the line AB with respect to if it's a front view, we are saying its angle from the horizontal plane, right? In the front view, its angle of inclination from the horizontal plane. Otherwise, line will be like this only, right? Is so much. So you can draw the line AB also. And the third input that you may get when coordinates of both points are not given is saying the length of the line is so much. That will be the issue here because you do not know the actual length of the line may be more than what you can draw here. So you can only draw a projected line A dash B dash. Okay, we'll come to this projection in a minute, but right now just think about drawing the line, a projected line, but need not be exactly at the ends A and B. And please, you're mildly confused, but just hold on with me for a minute. Okay, we are just talking about you're drawing the line reasonably well. At least point A is properly marked, and you're able to draw a extended line through because the angle is given to you. Okay, how to find the point B, we will talk about in the next slide. So for the moment, just mark also the points B and B dash. Let us say those are the projections of the point B on the horizontal plane and the vertical plane. So we will look at that. And mark the third final statement in this slide, which says that the projected length in both top view, either top view or front view, are now less than the true length. Earlier, it was equal at least in one view because the line was parallel to one of the planes. But now line is not parallel to any plane. So its projected length will always be less than your real length. Obviously, again, if you apply cos theta or cos phi principle, they will always be less than the actual truth. Now we'll talk about how to draw these things. Okay. Prabhat, anytime my line goes off, someone should be prepared to take off. Okay. Hello.
Okay, sir. Okay, sir.
I'm just worried. It's going smooth, but my only thing is my battery is now almost off. I didn't expect this to happen. I don't have a charger here. Okay, so let's go slowly, step by step. Point AB, okay, and what I'm going to do is, let's say that I'm able to draw the projections of the point AB, okay, and what I'll do now is I'll start doing now the projectors, and projectors are always lines through a point parallel to, let us say, the vertical plane or horizontal plane. In this case, XY line represents both horizontal and vertical plane, intersection of that. So as long as you draw a line parallel to XY line, it's a projector through the point A, let's say here. I should have marked A here. What I'll do is I'll just do this because I can see that I can refer to these points as A, B, C, D, and so on. So what we do is first what we have done is we have marked the point A, and then because we know the angle of inclination with respect to the horizontal line, we are able to draw this line. Okay, this line could even be drawn extended because you don't where it ends. But if you know the projected length of the line, then you know where to stop here. Okay? Otherwise, you cannot. You just have to draw the line there through the thing. Now, what I'll do is, and just think for a second that this point AB is there, line AB is there, but just for a moment, look at point B alone. The projection of point B in the HP, the point below is in the horizontal view. In the horizontal plane, it is top view. Top view is always B, right? Small b. Okay. The point B in the horizontal plane, if I draw an arc, okay, I'm just going to draw the arc here. Okay. What is this happening here in this case? And let me put this. Unfortunately, I just need the. Don't look at the green line for the moment. Just look at the point, the lines AB, small line AB. Okay, on the right side picture. What is this B here? This B is nothing but this point capital B projected onto the horizontal plane, right? That is my top view. Now, if I keep this, if I use a compass and I draw with the compass, if I draw an arc, now no matter what I do, the length AB and AB1, the length are same because I'm using compass to draw the line. Okay, so that's what I'm doing is I'm basically doing that. And once I do that, come to point B1, I'll draw one more projector now perpendicular to XY line. So I go to the other side. Similarly, I have a projector. So did I say 4 projectors? One is projector from, so line AB is known, line A dash B dash is known. I have drawn a projector parallel to XY line through A, through B, through A dash and B dash. Okay. If I didn't say that, I'm just adding that now. Okay. And then what I do is I take a compass and draw this line B to B1 and then use that to project to B dash, B1 dash. And follow that now in the 3 dimensions. This is my point B, okay? And from B, I go to my B1, and from B1, I go to the other side, XY line, okay? And from there, I'm projecting it to this one, which is what my B1 dash is, okay? Now, B1 dash, okay, in some sense, did I dot, would be the true length of a line. Just think for a moment why I'm saying that this green line is a true length of the line. Okay. Or hold it in your mind if I don't understand that, we will just switch to the other side of the thing. It's the same thing. Okay. Same thing now. I'm doing the other way now. Okay. Instead of going from the top view to front view, I'm not going from the, let's say the front view to top view. What I'm doing now is this. This is my line AB. Okay, it's a projection on the on my front view is A dash B dash. I use a compass to go from B dash to B2 dash. Okay, use the projector to go to the other view. Always remember that the views are normally not, these planes are normally perpendicular to each other, but for drawing these things, we are making them, we are rotating the horizontal plane. Remember that. As long as you remember that, you know what is actually happening with these projectors. Okay, and so if you map from left side to right side, I go from A dash to B dash first, B dash to B2 dash first. By drawing a projector, I get this new point B2. Okay, I wish I had marked it on the left side also, then it would have been very, very, very clear. We'll just go, now we'll just combine both, and now it will be very clear. What I'm doing now is that I did two different constructions, graphical constructions, one after another. But now I'm combining both in the same view, and this is what it is all about. So what do? You start from your, again, maybe I said that in the last minute, but you can start either from your front view, A dash B dash, come to your B2 dash, draw the projector, and come to B2, which is nothing but the intersection of the of your projector line and this projector line. Similarly, on the other side, you are taking this the line AB, small a, small b, using the compass to go to the, in a sense, parallel to vertical plane, parallel to, this is my top view, so my parallel to vertical plane. From there, I come to the projector of the parallel to horizontal plane, and that intersection gives me my B1 dash. Okay, and these two, in a sense, the angles, okay, become your true angles instead of the apparent angles. What is given to you, saying that this line AB is inclined to 30 degrees by vertical plane, 30 this thing. This is now giving you the true inclination of the line. Okay, and this also gives you, this green line will give you the true length of the line, and true length, these two green lines have to be equal. Then you know that your construction is okay.
Sir, true inclination with respect to what?
Sorry, once again.
Sir, true inclination with respect to what? You are not specifying which plane. Are you specifying?
Maybe I'm not. Maybe I'm saying a different way. So, Prabhat, anyone can say this in a different way, what I just told? If I say, I'll be saying the same.
May I?
Yeah. Yes.
Yeah. So the true inclination, you can take it, if you see in front view there is one true inclination, and in top view there is another angle which you get it as a true angle. So in both the views, when you rotate the line A dash B dash to its true length, that is A dash B1 dash, you get one true angle, which is that is a true angle with respect to horizontal plane. So since this is a front view, you get true angle of the line with respect to horizontal plane. And when you come to top view, and the same in the similar fashion, if you rotate this AB to AB2, you get a true angle with respect to vertical plane. So two planes with respect to two different planes, you have two different angles. So those are what we represent it as theta and phi. It's more easy if you imagine graphically how it's coming.
Okay, I got it.
Sir, I have another doubt. So I understood this, that how this theta is the actual angle with the horizontal plane and so on.
Yeah.
But sir, then what was the angle at which we made this A dash B dash? As you said that we were given the coordinates of point A, so we were able to project in the two planes and get the points A dash and A. Then after that we were given the angles, and based on those angles we made these two orange lines. Based on those angles were given. So if they were not the correct angles, then what were they? Like, how did we make these orange lines then?
So those are actually projection angles. So they are represented with alpha and beta. So there are particular notations for them. Alpha for top view or front view, I don't remember exactly. So those are the angles we obtain from projections. So those are not the angles which we actually see in 3D. But when you project it into a 2D, only then you will see those angles, alpha and beta.
Okay,
Oh, so
so
does that, yeah, so
yeah,
does
go
that
ahead.
mean that like in the previous slides, there was this figure which was showing a line inclined to both the planes, which was not parallel to any plane. So when we had drawn those two projections, so the two angles were not the actual angles with the horizontal and the vertical planes. They were different, like they were projection angles and they were not the same as the actual angles. Is it so?
Yes, yes.
Oh, all right. Okay. So we would be given those angles, and based on that, we have made these two orange lines, right?
Yes, yes. Like it depends on the question. Sometimes you will be given theta and phi. You have to find out alpha and beta or a dash b dash. You'll see the questions. If you see the questions, you'll know how they'll be asked.
Okay. Okay. Got it. Fine. Thank you.
To follow this, I'm not understanding when we had a dash b dash, how was the angle different from theta and phi? Like it should be same, right, when we are projecting?
Yes, like as I said, just a minute, if possible, I'll show you.
Yeah, hello, am I audible?
Yes, sir, you are audible.
So basically my mobile has run out, so I just switched back to IIT, but I think it is breaking all the time. I think it looks like, okay. So, so I think one of you should also project. Prabhat, should you project also? I don't want this to be breaking so many times. Hello,
Okay, sir, I'll do that.
can you
I'll
project
share.
that? You have
Yeah,
the
I'll share.
latest. Yeah, okay. I said project that in a pun intended, project a slide. From our three-dimensional world to your Microsoft Teams 2D world. Prabhat, can you?
Yes, I'm doing it.
Actually, by the if my screen is still visible, students look at this. Just look at this small exercise. I think it will be a little more clear to you. Prabhat, just project this slide in case your PPT comes up. Student, just do a quick exercise.
Yeah.
Okay, that's how we give the problems to you. So length of a top view is what your okay. Basically, length of the line is given, but length of the top view of a line is 50 millimeters, right? And line is inclined at 45 degrees to horizontal. And one end of the line, which is essentially your coordinates of your, let's say, point A is given. 12 millimeters above HP and 25 millimeters in front of vertical plane. Okay. Now you draw his projections and find its true length. This is, by the way, parallel to one of the views. It's easier than the double inclination to both the planes. Students, take your sketch and then.
I have shared, sir. I have shared my screen. You can
Okay,
unshare.
good. So anyway, you are shared, so that's good. Thank you for that. Yeah.
So we
So
are unable
students,
to see the diagram.
No, I don't want to. This is your diagram is a solution. So if you're seeing, just forget it. Do it yourself.
Fine.
Yeah.
So everybody done? Can I move on to the solution?
Wait for.
Okay, so whosoever has done, maybe you can just check your like solution. Is it coming like this?
And if your answer is not the same as this, figure out what went wrong also. As important to figure out what went wrong, in case it is not the same. Can we have a thumbs up from everyone? If those who got it right. You have to evaluate yourself.
Hello,
Yeah.
sir. Couldn't we take the one end of the line as B dash, like the point B? Then how would we draw? Hello?
Yeah. Sorry, what did you say? Could you please repeat?
Yeah, in the question, one end of the line, that one end can't we take as the point B instead of A?
You can, but that will change accordingly. You know? The other end will change accordingly. I think one end of the line is 12 HP. So A,
Yeah,
B,
so
we have just written a name, no? So we can take, you can take anything, B, C, whatever you want. But
so
the figure, yeah,
figure is not.
the solution will come like this only. So that end should be coming 12 above HP. Okay.
Okay,
So here
okay.
it will be coming this 12 above HP. So whether it is B or C or A, that doesn't matter. And then 25 in front of VP, so that will come in this way, in this view basically.
I have a doubt.
Yeah.
Like in the question it is mentioned that the angle which the line makes with the horizontal plane, that is 45 degree, and in the figure we have made the angle of the projection with the horizontal plane to be equal to 45 degree. But as we discussed in the previous slide, so these two angles are different. So here are they same because the line is parallel to the vertical plane?
No, so here we are taking
Yes,
yeah, one,
yes.
exactly, yeah,
Well,
exactly,
it is
that is
parallel
parallel.
to one of the
Yeah,
planes.
sure.
The angles are same.
Yeah, that's why it is the same. Otherwise, only the apparent angle that would have been given, okay, not the true angle.
Yeah.
So
Okay,
that
Yeah,
was
okay. So
one
if
of the questions Shubham has also asked. Uh, so if there is a couple of minutes time, can I give a small explanation for that?
you can.
Yeah, go ahead.
Yeah,
My
you
line
can.
is still
Thank
breaking,
you.
so Prabhat, I think better to keep my mic off.
Sure.
Are you
Okay,
hearing
okay,
my
yeah.
deconnection sound also? I don't know.
Say
Yes,
this
sir.
is
Yes, sir. Yeah.
say this is the line, and right now, let us say my laptop screen is the vertical plane and the keyboard of my laptop is the horizontal plane. So say this is the line which we are talking about. So this is right now parallel to my laptop screen. So you can see the exact angle directly straight away. But then when I start rotating this, see carefully, when I start rotating this, there is an angle which when you cannot see an angle at all. There is this particular position of the line where you cannot see any angle. So it doesn't mean that it's not making any angle, right? There is an angle here. So which you can see that angle only when it is parallel to the vertical plane. You can see it in front view. So that is why true angle and the projection angle are different. Shubham, am I clear? Did you get me?
Yes, you are clear. I got.
Yeah.
But can you explain in the case where you don't rotate the scale exactly to 90 degree but keep it at some angle? So then how is
Yes.
the projection angle?
Yes, that is also the thing. So here this is the angle. This is the angle which the line is making with horizontal plane. So when you go to some other angle, see now you can see you see a different angle. But then I am keeping this angle constant with respect to HP horizontal plane. Do you see a different angle? You see a much bigger angle here. This is the angle which you see. That means in the projection you see a different angle, but in actual this angle is same.
Can you bring
I
it back
can't see
again to
your.
the parallel side just to
Yeah,
observe? Okay.
this is the
Yeah.
parallel
Yeah.
side. So I'll try to keep my both hands at same height as far as possible. So this is
Excuse me.
so now
Excuse me.
you
I
see the
can't
angle is
see.
changing.
Excuse me. I can't see the video like properly. It's lagging a lot.
You just click on my video screen, so it'll pop
Yes,
out for you.
I have pained your video, but it is not in running smoothly.
Sorry, but I'm
Same
at
for
IIT.
I think it's clear, like it's clear for me.
I'm in IIT connection only, but I can't help with the connection. So if you people understood what I am demonstrating, then you can help out your friends also. Anyone or no one could follow?
Able to follow.
Revant, your video is clear. You can explain. Like it is from his side, I guess. Like the network issue.
Okay, so that is it. So even if at least 20% of the people can catch, then you can explain to your friends. So see, this is, say suppose I kept it this at a 30 degrees angle, 30 degrees with horizontal plane. Now I am rotating it at the same angle. See, now you can see it appears to be 45 degrees, isn't it? It appears to be 45 degrees for you.
Yes, yes.
But in actual, I am holding it with the same 30 degrees only. So that is the difference, why it is happening. So when you move it, the hypotenuse length will change, keep on changing. The hypotenuse length will be keep on changing. So the angles will change. The angles with what you see, what you project changes. That's all.
Also, can you explain how to calculate the true length?
So it's
You
the
just-
same. So it's the same thing. So right now I'm showing only with the angle. This is parallel to vertical plane. So when you have this here, you will not be seeing true length in projection. So what do we do is we just rotate this parallel to vertical plane, and then we project. That is a true length, and that is where we get an angle theta or what was that angles? That was theta.
Phi, theta and phi. Yeah.
So when you have a line which is inclined to both the planes, you rotate this and make it parallel to vertical plane. For once you make it parallel to vertical plane, and then what you do is you also rotate in another direction and make it parallel to horizontal plane. So that is how you get theta and phi, and both the true lengths are same.
Yeah, got it.
Yeah.
Yeah. Hello.
Yeah, go ahead.
Yeah, can you explain where the origin of the system lies?
See, if we have an 8-quadrant system, then there is an origin. In here, there is no specific origin, but there is XY line is the basis for our drawings. The whole XY line, we treat it as an origin.
Okay, so if a point is given with its coordinates, we cannot find the other point with the other point's coordinates, right?
No, not exactly coordinates. You can give it in terms of how much mm it is above HP or in front of VP in those terms.
Yeah, that's fine. Okay. Thank you.
I have one small question. Like whenever we rotate, like let's say we rotate with the angle phi and make it horizontal, and we rotate the angle theta and make it horizontal. So in both cases, the true length will come out to be the same only. Like
Yes. True length is always the same.
okay.
True length is always the same, and you have to keep one more thing. A dash and A will always lie on same line, and B dash and B lie on the same vertical line, because it is the same point which we are projecting on two different planes. That's it.
Okay.
I think we can.
Thanks, Revant. Maybe we will move on.
Yes.
I just have a small doubt, just a small confirmation. So as you were saying that like the projection angles is different, so it is because the height of the right angle triangle remains the same and the hypotenuse changes, so the angle changes, right?
Yes, exactly.
And like in the example which sir showed, so we were given the projection angles and we could find the true angle which the line makes. So can we also do the opposite?
No, I think that mainly it will be given the apparent angle, the projected angles, okay? Because we are
No,
drawing
no,
the
like,
projected views, no?
yeah, no, I'm not talking about a particular question. Like in general, is it possible to find is it possible to go the other way?
I'm not sure about it, but yeah.
No, can you repeat what do you mean the other way? Just say it in
I'm,
words so
I
we'll
mean,
start to visualize
yeah.
that. Yeah.
So, like, if we are given the angle which the two projections make with the other plane, so we looked at a way at how we can find the angles which the actual line makes with the two planes. So, not for this particular question, but in general, is it possible to go the other way around? That is, if we are given the actual angle which the line makes, so is there a way to find the angles which the projections make with the other plane?
I mean,
Yes,
theoretically, yes. My point there is that usually that will not be available. See, when that's the whole point about engineering drawing actually is that it is easier to see things in a perfectly front view, top view, side view, which are perpendicular to each other. The moment you see something in inclined direction, it's very difficult to measure anything. Okay, but Revant, you go ahead, you say something.
The same explanation, sir. We can proceed, but we need more details. That's all.
Yeah, it is more difficult basically. Yeah. And in a real life, that situation doesn't happen. What will happen is that you are seeing, front view, top view, side view, and you want to see what is actually the situation, real angle, real length, and so on, right?
Okay. So we would not be given the actual angles which the line makes. In this case, they were given because it was parallel to one of the planes. So this
Yes.
was a special case.
Which is easy to measure. No, it's easy to measure, right? Even
Okay.
I'm no issue with questions like this. So please, the more you ask, the more you are clear, the better it is. Revant or anyone else would like to go ahead with the next one also, the traces. Next slide. Mine is breaking simply every second. Go ahead.
Yes, sir, we will do that.
Yes,
we
sir.
will do that.
Yes, sir, we can do that.
So this exercise we will skip as of now, and we will move on to the next part, which is traces. Okay, Revant, you can go ahead. I'll share the screen. Okay?
Yes, we can go to the next. This is one more example. So traces, we are well aware in our 2D graphs and all, when we draw a line, a straight line, we have something called intercepts, y-intercept, x-intercept. I know, I think everyone are aware of what is an intercept. So here, what trace is something very similar to an intercept, but then here we are converting a 3D into a 2D. So that is the reason we need 4 points to exactly show what is a vertical trace or a horizontal trace. We'll see what is a vertical trace exactly means. So we have an inclined line here, AB. Everyone can see on the left side there is an inclined line AB, which is at an angle with respect to horizontal plane as well as with the vertical plane. So when we extend this line AB, so this line AB is intersecting vertical plane at a point called VT, and this line, the exact same line, when it is extended downward, this is also intersecting the plane HP at HT. So these 2 points are called horizontal trace and vertical trace, HT and VT respectively. So in 3D, we just extend the original line AB and we obtain HT and VT. So how do we obtain it in projections? We'll see it later on. But first, let us cover a few more details. What is V and H also? So there is VT. As we can see, VT is on vertical plane. Okay, remember, VT will always be on vertical plane, and HT, horizontal trace, will always be on horizontal plane. So right below the VT, vertical trace, there is a point V which intersects the line XY at V. What is that small v represent? So when we project the line AB, we have the line AB projected onto horizontal plane. So it will become AB. Obviously, it will become AB. So when this AB is extended and it meets XY line, that point is small v. So that is small v is the projection of the vertical trace. So I'll just repeat this. Small v is the projection of the vertical trace on the XY line. Similarly, horizontal trace. There is a projection for horizontal trace also on the XY line, which is represented as small h. Am I clear, or do you want me to explain everything again? We'll go through an example. We'll go through an example in the next slide. I think if you have any more doubts, we'll deal there. So we can yes. So it's one more example. So we have projections. One is front view, one is the top view. So which one is the front view? A dash B dash is the front view, and AB is the top view. So now we see that to get traces, the first thing we need to do is we need to extend the actual line. But then here we have only projections. So let us start and extend projectors only. So we have extended A dash B dash. It will meet XY line at some point. Don't just forget what is H and what is V as of now. So A dash B dash, we extended it and it intersected XY line at small h. And there is top view AB. We have extended AB also to it intersected the XY line at some point. Okay. Now let us go back to basics. So what is a vertical trace? Let us see first what is a vertical trace. Vertical trace is intersection of the line on vertical plane, and projection of vertical trace is small v. So this is the definition you need to remember. And similarly, the horizontal trace also. Intersection of the line with respect to horizontal plane is the HT, horizontal trace. And projection of HT on XY line is small h. So if we go back to the previous slide, sir, can we go back to the previous slide, Prabhat Bhaiya? Yes. So see here on the left side, see on the left side. So we have HT, we have obtained HT, we have extended the line AB, it met HP at HT. And we have drawn a projection line from HP to XY line. So this is small h. Here, observe carefully, this small h is actually lies on the projection. Which projection is it? Front view. This is a bit tricky. There are so many things to be interlinked. So the front view line, when it is Prabhat Bhai, can you show it with the pointer? Yeah, so the front view is there. There we have front view. So when we extend the front view, then it intersects XY line at the exact same H. So we can say H is an intersection of both front view extension or projection line from horizontal trace. So now we go back to the next, we'll go to next slide. See here. Now what did we just see? When we extend the front view, we get H. So A dash B dash is the front view. We extend it to meet XY line. That is labeled as small h. And we have extended AB. AB is the top view. When we extend the top view and it intersects XY line, it intersects at V, small v. Now when we have seen H is a projection of HT, V is a projection of VT. So now we just draw the extension lines from H and V. We just draw the vertical extension lines from H and V. Wherever these two lines meet the opposites, Opposites. What do you mean by opposites? V is obtained from top view. So this line has to meet the front view. That is VT. Coming to H. How did we obtain H? It is the extension of front view. So the projection has to meet the top view. That is HT. So did all the steps connect to everyone? There is one more example on the right side. There is another example on the right side. I'll explain this also, and then we have a small example problem which you can try. Yeah. So on the right side also there is a front view. A dash, B dash is the front view. AB is the top view. So just forget VH, VT, HT, or just keep your hand so that you don't see them. Now you extend A dash, B dash. What is A dash, B dash? It is front view. So it intersects XY line at small h. So this is the step 1. And there is top view AB. So now you extend this top view AB. It will intersect XY at a point which is nothing but V. Now we draw projections from V and H. You just draw completely vertical lines, no problem at all. Those are the construction lines. You can draw how much long ever you want. So you just draw the extension lines from V and H. So this has to intersect the other projection. So V will intersect V extension line from V will intersect the top front view. Then we get VT. Similarly with H also. From H there is an extension line which will intersect the top view. That is called HT, horizontal trace. So that's it. Yeah, so these are something which you have to mention when it is asked in the question. So HT and VT, they're always on the planes only, on horizontal plane and vertical plane. But when we open the when we rotate the horizontal plane 90 degrees, then they appear to be on our page, above XY line and below XY line. So depending on that, you have to write down where is HP. Is it above or below, like that? Similar to the point. How we mention a point A, it is 20 mm in front of VP, 40 mm above HP. In the same way, you have to tell where is HT, where is horizontal trace HT, and where is vertical trace VT, observing the diagram. So in figure 1, we see that HT is above and VT is also above. So from projection of points, you have seen how do you get projection of points, like above X, like when front view is above and top view is below, it is in first quadrant, right? So something like that you have to mention where is HT and VT also. So this is something you have to write. HT is behind VP. So what does that mean? Behind VP means, what does that mean? I'll just show you what does that mean. What is HT is behind VP. So this is the XY plane. Okay. So you have the line like this. Say it is like this. So it will first intersect the vertical plane. Let me show you here. And then it will pass through here, and then it will intersect the horizontal plane behind the vertical plane. So that is what is HT is behind VP. So as I shown, VT is above HP. It is intersecting vertical plane first, and then it is intersecting horizontal plane. So that's it, example 1. And what about the second one? HT is in front of VP and VT is below HP. So what does this mean? So this means there is a line something like this. There is a line something like this. First it will intersect horizontal plane, and then it intersects the vertical plane. So when you rotate this system, when you rotate the system like this, so you are getting horizontal trace here, vertical trace is already there. So that's why we are getting HT and VT below the XY line. And so we have to write HT is in front of VP and VT is below HP.
So just to confirm, so there are no other possible configurations, right? Like there cannot be a case where HT is front of VP and VT is above HP, right?
No, it is possible. I'll show you one such example. Like we have seen in the previous slide only. Prabhat Bhaiya, can you just go back? Yeah, see here, in this one, we can see VT is above and HT is below XY line. And when you transfer this back to 3D, you can see here on the left side, VT is above HP and HT is in front of VP. Understood? So if the line is not completely in the first plane, in the first quadrant, then there is a chance you get traces on the line itself. Do you get me?
Yeah, got it.
So, okay, we'll go to the next slide. So this is one exercise problem you can try. So see here, I think it's better you try this problem on your own. But I just wanted to tell you one thing here. See, the line itself is intersecting HP or VP. So that is the reason we need not extend front view and top view lines to get V and H and then get VT and HT. Okay, here the line itself is intersecting the planes. That's why when you draw the line projection itself, you will obtain H and V. From there, you have to draw vertical traces to obtain vertical trace and horizontal trace on the projection, other projection. So this is a good example. You can try, your concepts will be clear.
Okay, we'll have to close the class because it already is close to 11 actually.
Yes. Yes,
what we'll do, students, is that I think a couple of errors which were in the slides, we'll fix them and share the slides with you maybe today itself. Okay, take a look at that. So that is for reference for what happened in the class. But also please go back to ND Bhatt book also, and there's a detailed explanation of, right from beginning of what I said. Class is more or less a snapshot of the book in any case, right? Plus we have given some home exercise which you can also try it out well ahead of the lab next Thursday. Okay, the more you kind of go through the book and kind of visualize mentally, the easier will be for you in the lab also. We also make sure the lab is reasonable question so we can finish it within 3 hours, in spite of any major issues, minor issues. Major issues anyway you can't do anything. Okay, so let's close the class. Thank you for your patience. TS, everyone, Revant, anyone else who helped out, Prabhat, thank you for that. I hope at least now my line is not breaking. I don't know. It was a bit issue today. But thank you and see you in the Thursday lab class. I think next lab, I think, is not going to be there because next Thursday, Friday, both are holidays. So you have plenty of time not only to practice today's class, exercises and so on, and also read up from the book. Maybe read up a little bit about next chapter also, because when we meet next, the following Thursday is when you do today's classes lab, and then the following Friday I'll talk about the projections of planes also. Following means not the next week, but the week after next week. So next week is both Thursday, Friday are holidays, so we'll be closed. Okay, so have a nice weekend, but don't forget what we said today's class by the time the lab, because lab is going to be after 2 weeks almost. So take care and practice. And
excuse me, sir.
Yeah.
Will you consider all the labs for evaluation, or is it like best n out of m?
I think we declared in the first class that we'll have 10 sheets and we'll take 9 out of 10 sheets, something like that. Okay, we are relaxing the rules a little bit, but not open. Total relaxing will not work. Any announcements like that we'll also put on the Moodle or something, so that everyone who has not attended the class also knows about that. Okay, so we'll